Today we're doing a multivariable calculus problem, or Calc 3 problem. We've got the value, we're trying to find the value of this line integral, so integral c f dot dr, where f is the vector field 2xy minus 7x comma x squared minus ey, and c is a curve that goes from 2, 0 to 7, 1. So the first thing we try a lot of the time is to parameterize the curve that we're given. The issue here is I really don't know any information about this curve except for the 2 points that it goes through. So I don't know if this is like a straight line or actually a quote-unquote curve. I like to think of it this way. So yeah, I can't parameterize this at the moment, so I can't go with a direct substitution right now. So what I would like to try is I'd like to use a tool, something that could help me here. And what I'm going to be working with today is these what we call equivalency statements. And as we have here, it says the following are equivalent. And for those that don't know what an equivalency statement is, it's a set of statements for which one statement implies the other, or one fails, the other one fails. So we have these 5 statements here, which are all true if one of them is true. So your first one here is saying that if your vector field is conservative, then this means is that the vector field is equal to the gradient of some function, some scalar valued function, lowercase f. I'm reading number 1. And yeah, this scalar valued function goes from Rn to R. The second thing is that the second condition is that the curl of f is equal to 0. And in other words, if you have a vector field which is in two components only, p and q, and made out of 2 variables, x and y, let's say, then it's equivalent to saying the partial of the first component p with respect to y equals the partial of the second component q with respect to x. So that's the second. The third condition is that your integral is independent of path, meaning that the value of the integral does not depend on the actual path that you pick. It'll come out to be the same regardless. Number 4 here says that the line integral depends on the function value at your endpoint minus the function value at the start point. Here function is again the potential function, the one whose gradient gives you the vector field. And finally, number 5 says that if you have a line integral if your curve is closed, C is closed, then the line integral is equal to 0. Okay, so I want to go ahead and try to use this. So the first thing I like to do is see if this is a conservative vector field, because if I can prove that, then I can use some of these conditions here in tools. So I'm going to go ahead and take my vector field and take the partial derivative with respect to y and with respect to x. So 2x and 2x. So it is conservative. What does that mean? Well, that means I can go ahead and use some of my conditions to compute. Now, for us, for computation of line integrals, 3, 4, and 5 are the conditions that usually work out the best here for you. Okay, 5 is not going to work here though, because we're not working with a closed curve. So it's either 3 or 4 that you can work with. Which one? There's some pros and cons to using 3 or 4. So let me start with condition 3. If your integral is independent of path, your line integral, what does that mean? Well, and how do we apply it? So what that means is you can pick any path that you want from the 2 points that are given here. So I had 2, 0 and 7, 1. Okay. And yeah, I could pick a straight line. I think that's probably the simplest thing to work with. And I found the equation of the line and parameterized that line as R here. 2 plus 5 t and t, 0 to 1 for t, inclusive of 0 and 1. And yeah, and I'd advise you to, pause this video and see why that is. And I'm going to go ahead and calculate that line integral along that path. So computing a line integral involves you composing the vector field with the curve components, so f of 2 plus 5 t here, dot it with dr, which is the derivative of each of the components with respect to t, and you will go ahead and do a dot product and this is right here is what you would have your result out as, and you would wind up with this huge integral. Okay, it's okay actually, you can put a lot of like terms together, but it's still somewhat a lengthy kind of computation here. The second method is by using condition 4, which is using the potential function. So this involves you finding, first of all, what the potential function is. I'm not gonna get into that because it's something for a separate day here. There's another video, but basically involves you finding the function for which the gradient is equal to the vector field, and involves taking antiderivative and such. But anyways, and I'll make a video about that. But this would be your function, your potential function. And if you find your potential function, all you would do is plug in your endpoints and your starting points into your potential function and subtract them from each other. So this is like a fundamental theorem of line integrals. This is what this is often called, because yeah, it looks a lot like the fundamental theorem of calculus, right? And at the end of the day, if you did all the math here, we should come out with this. So minus 215 over 2 minus e. And that is the result of that line integral if you were to do that as well. So either one comes out with the same value. So it's up to you which one you want to do, right? The first method with picking the path, usually the path, yeah, as I said, a path is a line that you could pick. It's fairly, easy to get the path, and fairly easy in terms of the actual like composition. The hard part is perhaps the integration, okay? That might take a little bit. On the other hand, with the other method, using the fundamental theorem of line integrals, you first of all have to find the potential function, which can take a couple minutes here and there. And once you do that, then you just plug in your endpoints and then subtract them, and that's it, okay? So that is how you handle the value of a line integral of a conservative vector field, okay? So often, there's excuse me, there is a way that you're going to be using this because, excuse me, because you were told that you just have 2 points, you're not given the curve, so watch out for that, where you'll be using conservative vector fields, okay? Because if we didn't have that here, we'd be if this vector field wasn't conservative, we'd be stuck. All right, well, thank you so much for your time, appreciate it.